Hi guys. So we are moving on a little bit. We've talked now a lot about recursion, and we also talked about algorithms. But now we're going to shift gears a little bit and talk about something completely different in some sense. But it is also part of discrete math, and this is so-called graphs. And this first lecture, I'm not going to make it too long. I'm introducing the concepts. We will busy ourselves with these graphs for a couple of sessions, but we need to know first, introduce a little bit of terminology and see what are graphs. Now, graphs are a fancier word for what we probably better know as, you probably know as a network. So, for instance, you could have a network between cities. Say you have here New York. It's not geographical. So that's one thing. It's an abstract rendering of a network. In other words, the vertices or nodes represent, for instance, in this case, cities, so New York City, and here would be Boston, but not in a geographical sense, just in a relative sense on how are they connected, how are they, let me allow me to make a couple of, so we have LA here, let's put Chicago here, well, let's put here Miami. Again, you see they are geographically not really make sense that much. And here, let's put here, let's see, Atlanta. Okay, so these are all rather big cities here. And suppose now I'm a company and I want to put some branches of my let's say I'm a transport company and I'm deciding, okay, some of these places I want to have a trucking route between them, and I decided, okay, I'm going to go from New York City to Atlanta and from New York City to LA, but I don't want to go to the south here, so I also go from New York City to Boston. Okay, and then so this would, for instance, be, and then perhaps I say, okay, so this is my first design. I say, okay, these are the four cities I'm going to serve. And so what is it? What is the two ingredients really? There are these dots that I make a little bit, and they are called nodes or vertices. That's actually the vertex. The plural is vertices. That's a bit weird plural, but it is because it's a Latin word. So that's what we call a vertex or a node. And then we have these lines, segments, and these are called edges. Okay, and when we see a graph like that, sorry, I should distinguish between my commentary and my. So let me erase this thing here. Okay, sorry. Let me go back to my graph. So let me do this in different color. Sorry, I should have done this in the so a node over a vertex, that are these guys. Okay, and an edge, that is these the connectors there, that are edges. Okay, that's what we call an edge. Okay, so that's a network that represents the trucking routes that I have between various cities. And say I'm expanding my company and I say, okay, I'm going to go from Atlanta to Miami, which makes sense. And then I also go from New York to Chicago and from Chicago to LA on the way. Okay, so I have expanded it and it is still a network. Okay, now it might be that at some point I decide, I said, oh, okay, Boston, fine, I need a bit more connections to Chicago, and I'm going to also go from Atlanta to Chicago. And I could even add a city and say, okay, why not add DC in here, and I'm going to go from Chicago to DC, and also from New York City to DC. Now, here already we see a little bit of a problem. I'm crossing here. And we're going to have to do this because very often it is impossible to represent a graph, so a network. The fancy word is graph, but let's call it a network for the moment. We're going to have to represent this in a two-dimensional paper, on a paper, right, or on a blackboard, but that's not always possible. That is a topic that we will not really discuss, but so in other words, when I have a crossing like that, I should imagine really that the crossing is actually this. that it is more like this, and that I go over it and like that. So a crossing of edges, if it's not at the node, it doesn't mean anything. Okay, it is just it doesn't represent any node. Nodes have to be like circled a little bit, or and have normally names. Edges, you see, don't have that much names, although we will also at some point start giving names to our edges. Sometimes it's necessary, sometimes it's not. The nodes also sometimes are named, sometimes they are unnamed, but in most practice, for all practical purposes, it's the nodes that is the information that we want to encode, and it's basically how are these nodes interacting, how are they networked, and that is what a graph does. Okay, so what is a graph therefore? A graph consists of two things: a set of nodes, of vertices, and that is this will be, we call this V, yes, V, sorry, okay, and on the other hand, as E is a set of edges. So what is a vertex? Is a point. It represents this point. So here V is LA, New York City, Boston, Atlanta, DC, and Miami. So what is E then? How do we represent an edge? And an edge is always a pair, a set of two elements, namely, so we have EF, where E and F are edges. Sorry, where E and F are vertices. So E, so no, sorry, no, let me not use E and F, let me use A and B. So an edge, so what is an edge? That consists of two elements, A and B, where A and B are nodes. A pair of nodes. So for instance, here, to represent this edge from LA to New York, I have LA, New York. So it's a pair of two elements. You say, why don't you write it this way? Because that's why we normally pairs like that, right? Yes, I will come back to this, but it is a slightly different object that we get. We get a so-called directed graph. If you write it with round brackets like that, what it means is this is the first element, this is the second element. When we write it in set notation, there is no first and second element. I don't know whether you remember this from Dixit Math 1, but a set is an unordered collection of objects. So just because I write LA first doesn't mean LA comes first. It's just two elements. And these are the endpoints. We call these A and B the endpoints of the edge. Okay, so I'll come back to the directed graph, but for the moment we don't have this, so I'm not going to put all of them, but for instance, if I want to put this edge in here, so let's call this edge E. So E, what does E look like? Let me write it this. So this edge E here, so see, sometimes I give a name to an edge. So E is what? Well, it's the pair consisting of the two endpoints, Atlanta and Miami. Okay? So that is how we often, how we can write down what a graph is. But very often, and that's the whole point of a graph, is it's a picture, it's visual, and we don't have to list all the nodes, and we don't have to list all the edges. You can see it. And so it's a way of storing information in a pictorial, in a visual way that we can much quicker assess it than if I would write down all this set here of edges, and I would have to say, let's say here another one would be this one, right, between Boston and New York. And you see that the notation gets kind of a little bit cumbersome, right? All these parentheses, all these brackets and parentheses and commas and so. Whereas the picture is very clear. Okay, so a graph is a network. Same thing, and it consists of a set of vertices or nodes, and these nodes are connected by edges. Okay, now there are of course many options now. This is the simplest case, and in fact this is what is called a simple graph. But what are slight modifications? First of all, let me go back and make my picture again here. So we have LA, and we have New York City, and we have Boston, and we have DC, and Chicago. It doesn't have to be in this, look, it doesn't have to be in the same order or the same thing. So I'm just going to put a couple of there and whatever here, Atlanta. So let's put these guys here. And now, for instance, I'm designing a network and I want to put network connections between these cities. And I say, okay, New York City and DC, that I'm going to put one network. But after a while, you notice that this gets a little bit overused because there's so much traffic communication between New York and DC. I'm going to put a second. And perhaps at some point I decide even to put a third. Now, LA and New York City is rather far, so I'm not going to put too much between them. New York City and Boston, okay, after one is not enough, so I'm going to put a second one here. Atlanta, I'm going to connect that to DC, but only one. And Chicago, I've decided I'm not going to put inside my graph yet. So this is another thing. You can sometimes have a node that has no edges coming in. We will talk about later what that means, but that is allowed. So it's not necessary that every node has to have an edge coming in. Also notice, by the way, there's no restriction on how many edges come in here. So you see New York City has quite a lot of edges coming in. Boston has only one edge coming in, or Miami. Again, we will talk about this particular phenomena, what this means, and we will analyze this. So keep in mind, all that we are doing here is presenting different graphs, but we have to analyze them because there are kind of different things happen in these graphs. That is something that comes in the next lectures. Okay, but you see here what is weirder now is that we have several edges between the same nodes. That is something that sometimes happens, although we will not study it much, but you have to understand that these things can happen. That is possible. Some networks are designed that way, that there are so-called multiple edges. We call this a multiple edge. And then how do we represent this? You might say, okay, so remember, putting the two endpoints, this gives me an edge. So this is the edge between New York City and DC. But how do I indicate that it actually are not just one but three? Then I say with multiplicity 3. So the multiplicity says how many of the same endpoints are connected by edges. So we have, in other words, 3 edges between New York City and DC, but they're assumed to be different edges, right? So there might be different networks, different, I don't know what or how that would work, but okay. And sometimes even what we can have is a network from the city to itself, for instance. There might be various reasons that we want to do that. Sometimes it is for checking backups, something like that. So and this thing has a name. Let me put it in red here. So when we have an edge that goes from an endpoint to itself, we call that a loop. Okay, so a loop has only basically one endpoint. So loops, therefore, are really represented. So this would be the loop New York City. You could say, why don't you write New York City, New York City? Okay, so let's think about it. So why don't I write this? Because it's the same thing. A set is an unordered collection of objects, and it doesn't matter how many times you mention an object, it's only there once. So this as a set is the same as that set. So writing it twice or once does not make any difference. And therefore, if that's the convention, so why write it twice if it is the same as once? Now, of course, granted, this is, you have to know that this remember what is a set with one element is called a singleton. So what is a singleton is a loop, whereas a 2-element set is a real edge. Now, loops are sometimes allowed, but often they are not allowed. Okay, so we have now talked about multiple edges, loops that are a little bit weirder things that can happen, which we mostly will not consider. So keep in mind, this is the most common thing that we will study, but now I'm giving a little bit more various possibilities, and we will look at examples once I introduced all the possibilities here. Now, this is what a graph was. But now we suppose another thing. Okay, let me make a different kind of graph here. So suppose we have this here, and this is Facebook pages. So this is Facebook page of my Facebook page, which I never use, so don't go look for it. And this is my wife's Facebook page. She's also a professor in City Tech, so you could try to figure out who she is. And then I'm going to put some initials here that don't mean anything. So let's LV, and let's say Xavier Xenophobe, and Mr. Oh, let's put the Donald Trump here, Donald Trump, and let's put here Joe Biden, since we're doing being political. And then we have here also I don't know, another guy. So HH. Okay, so a Facebook page very often, well, you can be friends. How you would, if you're friends of each other, for instance, me and my wife are friends, and I think that's my only friend, but my wife has more friends. Let's say this is a colleague of her, and this is another colleague of her. She is definitely not a friend with the guy in the left here, but she's a friend perhaps with this guy, although she is not really, but okay, and this HH, she doesn't know either. So this would be, for instance, all the edges that go from this one Facebook page, PP, to the various Facebook pages that I've listed. Of course, there are many, many more, but I'm just giving a sample of Facebook pages. Okay. Now, for instance, Xavier actually is interested in what our president has to say, but he wants to hear what both presidents have to say. And this HH says, no, I am a big fan of my president, and I'm only going to look what he does. So we could have this thing. Now, this is not really how things work, really, in the sense that, okay, it's true, a friendship relationship is mutual, but very often it's somebody initiates the quest for a friend. So in some sense, it is somebody allowing another person to view his material. So let's put it this way. So it's, instead of saying friends, let's say we have an edge between, see, myself and my wife, if my wife can refer to my page. So if my wife refers to my page, there would be an arrow that way. If I would refer to her page, of course, I have to then make a difference here. If I don't put an arrow, so the arrows here are now what I'm adding. They give a direction. So what I'm trying to talk about are now directed graphs. And what this means is, perhaps rather than a Facebook page, let's think of a home page. And this is when there is a link from one or just any website, and there will be so if these are websites, represent websites, home pages say, then there is a link from one, and directed arrow means what? That this page links to this page. But often, of course, it happens that a page links back. But for instance, this Xavier here is linking to Donald Trump and to Joe Biden, but neither one is going to link back to him because, okay, these are small-time people, so they're not linking back. Okay, and the same here. And perhaps Joe Biden says, okay, I want to be collegial, and I link to this Mr. Donald Trump here, but Donald Trump says, no, I have nothing to do with this guy, I'm not going to link to them. But for some reason, he's interested in this person, and this person is not interested in him, so we have something like that. And then this guy says, okay, I'm linking to myself just for the fun of it. Okay, so what you see here, okay, sorry, there are a couple of arrows still left, right? So suppose that this guy links also to my wife's page, and this guy, no, Biden is not going to link to, that's not going to happen, right? But the other way around, perhaps. And then we have also a link, say, no, let's do it the other way. Okay, suppose that is, we have now a directed graph in which all the arrows, in which all the edges have become arrows. So directed graph is an edge is now an arrow. In other words, it has a direction, and therefore, like for instance, if let's put in this this edge here. So let's call this edge, I'm going to use different color. This edge, let's call that E. How is E represented? Well, now I'm going to write the originator, the beginning point first, and then the end point second. In a directed graph, in an undirected graph, so that's a graph without direction, without arrows, we call both nodes, we call them endpoints. Kind of because it doesn't matter where you start or where you end. Okay, that's kind of, we could have called both also beginning points, but endpoints is a shorter, so we say endpoints. However, we cannot use that terminology in a directed graph because there is really a beginning point and an end point. There's one start point and one end point. Well, there's one exception, of course, a loop. Should I put an arrow on the loop? Not really, right? Because it doesn't matter. But it's the same end and end point. So loops are sometimes considered, sometimes they are not allowed. Depends a little bit on the type of graphs we see. Notice that whereas in the original picture there was a connection between my wife's page and me, because we obviously refer to each other. But if I need a directed graph, I have to make a distinction between my wife referring to me and me referring to her. So that's why we have here two going in two directions. Okay, so this is not considered a multiple edge. By the way, so it is also possible to have multiple edges, which is of course also happens if you say, okay, somebody's homepage can have several links to the same page. Just because I want to make sure that you don't miss this link and I repeat it somewhere else, go to that page, and then a little bit later say, but if you want to know more, go to that page. So it is possible that in such a diagram, in such a network, in such a directed graph, you also have multiple edges. I don't want to draw them, it gets really messy. There are examples in the book. Okay, so this is all the introduction of the terminology that I want to talk about, and then there are so many different types of graphs, that situations that can be represented by graphs. So, for instance, the acquaintance graph. Acquaintanceship graph. That means we have a bunch of people. So I have Anne and Bob and Cecile, and we have Derek, say, and we have Eve, and we have Farhad, and we have Johnny. Let's say that. And so what I want to do now is the acquaintanceship graph is, there is an edge if they know each other. Of course, if one knows the other, we kind of assume then the other knows the acquaintance means both way, right? It's different than knowing somebody. I know Donald Trump, but I'm sure that he doesn't know that I'm existing. Okay, and so that would be a directed graph if you would have to mimic that, if you want to have to mimic that, if you want to image that. But if an acquaintance is something where both people are said to be friends, or at least are acquainted to each other, they know each other's name. Let's say somebody is in an acquaintanceship relation exists if they know each other's name. Okay, so Anne and Bob know each other, and Anne also knows Derek. Anne is very popular. She knows also Cecile and Gianni. Eve knows Farhad, and Farhad knows Cecile, and they know each other. And then Bob knows Gianni, and Bob also knows Eve. And say, okay, let's make it that way. So that would be representing this information. Now you could say, why would we do that? And obviously, I can only talk about this once. Let's put one more guy and say, let's put a guy whose name starts with an H. I don't know anybody. Perhaps you know somebody, and he has no connection. He doesn't know any of these people. So what I'm trying to say is, okay, look at the graph like this. Just looking at this graph, we see that certain things happen. For one thing, we see that there is a kind of people that are not connected. That can be information that is useful. Okay, what is also can be useful is that some people are kind of well known, whereas other people are lesser known. These have only 2 acquaintances. He has 3. So we will kind of want to measure the number of acquaintances that somebody has. That is determines on how many edges comes in. So that's another thing that we will consider. Okay, I'm going to draw a couple of examples. I'm not going to draw everything in the textbook here because then there's no end to it. There are many, so please read carefully all the textbook. It's all rather light reading to see all different types of graphs. I'm going to concentrate on the graphs that we mostly will see. The two types of graphs that we will be interested in as are the graph that I just draw. It's an example of a simple graph. If you want to know what exactly is a simple graph, no directed arrows, no multiple edges, and no loops. And what I also am interested in is a simple directed graph. That would be a graph, well, I guess then delete this loop. Or directed graphs with, again, no multiple edges, no loops. Okay, these are the two objects that we will really see. Although, as I said, in reality or in real life, there are sometimes need for more complicated variants. Here's an example from computer science. I'm taking this. So in a program consists of various steps. Now, okay, I'm going to do a very extremely simple example, and it is a bunch of assignments. So the first step is assigning 0 to value a to 0 the value 0, b the value 1. Then I'm going to declare c to be a plus 1. I'm going to declare d to be b plus a. I'm going to declare e to be d plus 1. And the last declaration is that e is c plus d. Okay, so these are steps in a program. Now imagine instead of 6, we have 6,000 of 6 million of these steps that have to be carried out. And what you can do, you can put this in one single program, and this is what's so-called sequential programming. But it might be advantageous to do certain tasks simultaneously. This is called parallel programming. But then you have to be careful. Okay, imagine you want to say, okay, each of you guys are carried out by a different computer. So one CPU is doing statement 1, the other one is doing statement 2, the other one is doing instruction 3, and so on. But you see already problems, right? How is this guy going to carry out his instruction? He doesn't know what A is. So to be able to carry out S3, we need to first have carried out S1. But we don't need S2 for that. So we can have skipped S2. So this is what we call a precedence graph. So a precedence graph. And so, for instance, you have S1 here, the first thing, that is necessary. So we put an arrow like that. You could debate on which direction the arrow should go, but I'm going to write them in this way. I'm following the book. That is, S1 precedes S3 in the sense that S1 has to be carried out before S3, otherwise it doesn't work. Or you get the wrong value, by the way. This can also be, right? If I do a step where, it could be, right. In S3 could be, for instance, the assignment A is A plus 1. A is being redefined there, or even the statement A is 2. So you have to be careful. We have to that these things that you don't overwrite information. So okay, let's try to analyze this further. Now, what about S2? Let's put S2 somewhere here. As I said, S1 does not. You don't have to carry out S1 when you carry out S2, neither S3, but for S4, okay, S2. If you want to carry out S4, you have to first have done S2. Okay. Because why? Because S2 refers to B, and in S4 we need B. But we also need A. So we also have to have carried out S1. So we also have this S1 here. So we have this. Now we should be very careful when we draw this graph. Do we need S2 for B? Yes, we said that already. Do we need S3 in order to carry out 4? No. It uses A, but it defines C, which is not used here. Okay? This one also doesn't uses C, but it uses D, therefore it needs S4. So S4 goes to S5. Okay. Now comes something that is important and is also something that we will study later is, let's think about S1 versus S5. Does S1 have to be carried out before S5? Yes, because this is already clear from this picture. S1 has to be carried out in order to carry S4, and S4 has to be carried out in order to carry S5. So, in other words, we can follow these two arrows and we get an arrow that way. We will give later a name to this property, and this is called transitivity. So we also need this. Okay. What about S2? Well, for the same reason, right? We also need an arrow there. You see already, my arrows, first of all, my edges are not necessarily straight lines. I just need to draw it that it visually connects one to the other. That's the only thing an edge is. So an edge is not a straight line, although the word edge might imply that. It is a connector. Okay, so keep going. What about S6? Well, as far as S6 is concerned, it kind of relies on everything, right? Because C and D, S3, it needs S3. It also needs S4. Oh, it doesn't need S5. Because, okay, you say, wait, why doesn't it need S5? Well, okay, let me think about this, because, yeah, no, it doesn't need S5 because it doesn't use it. What we're looking for is elements that are used in order to define E. This uses C and D. Granted, S5 gives one value, S6 gives a different value on E. But that is just the oddity of this program. So, but it's not, we don't need to carry out S5 in order to get S6. In other words, we can, in another way of saying this, we can do this in whichever way we want. So, but again, we have to think about transitivity. If S3 is needed for S6, then S1 is also needed for S6. And if S2 is needed for S4 and S4 is needed for S6, then I need also an arrow there. You see, it gets kind of almost overwhelming. And notice that I already got a crossing here that which doesn't mean anything. Since this is not a node, it doesn't mean that it goes from S1 to this crossing point. No. S1 goes all the way straight to S5. Now, let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Whoa. How come I have one too many? S2, S4. I just want to make sure because it's so easy to forget something. S2 goes to S5 and S4. S2. And what about S6? Oh, okay, there's one there. Oh, I think I miscounted. I think I'm correct. Okay, so and therefore what this means is if you want to give this to parallel computers, 1 or 2 or 3, whatever you want to do, you have to make sure that you give this step on one and this one in there, but once they have calculated, when you calculate this, you need to get the information from both. So it gets kind of tricky to actually implement this, but it is a way of representing the problems. Okay, I want to do one more, because these are, I'm not going to assign many homeworks here, and there's a lot of homeworks in the text. I'll assign some homeworks, but the ones that I want to go over are at the moment we have nothing to really do. We just use them as fun tools. Okay, so this is the so-called niche overlap, and this is used in ecology. So the study of the natural environment. And what is this? So let me draw the one that they have from the book here. We have a raccoon, we have a hawk. So these are animals that live in a certain habitat, let's say a forest. And by the way, you can ask about what about the arrangement of these nodes here? You said it's not, when it's cities, it was not geographical. You kind of draw them randomly. Actually, yes. But when you keep looking at what happens is very often people tend to put them like a little bit in a raster, a little bit on the same line, like. That's probably also because it's much easier to put it in print. Of course, drawing is much simpler, right? We don't need, in fact, it is harder to stay on the same line, as you see here. I was supposed to stay on the same line, but that's not necessary. It's not necessary. It doesn't matter. That's the whole point. So keep that in mind. So what I'm missing, a shrew, which is a kind of a rodent, also a mammal, I think. There's a mouse, and we have a woodpecker. Now we are, I know we are all city dwellers, so we don't know many of these animals. But apparently, so what we have. So what is the niche overlap? There will be an edge between two of these animals if they compete over the same resource, same food resource. Okay. So, for instance, a squirrel and an opossum probably would argue about nuts. They want to have the same nuts. I don't know exactly what it is that a squirrel and a crow are interested in. Crows and hawks, probably little mice or something like that. Now, it's not predator. It's not a predator graph. So you might think, oh, there has to be from hawk to mouse. No, the hawk eats the mouse. It's not that the hawk eats what the mouse eats. This is what we're trying to mimic here. So we have an edge if the hawk and the crow eat the same kind of thing. For instance, the seeds. Owls also eat mouse, so they probably compete with this, and owls also crow. Possums seem to also be wanting the food that woodpeckers eat. Woodpeckers also like what squirrels eat. I'm assuming there's also nuts about it. Raccoons, well, raccoons like what hawks eat. I don't know what it is exactly that they want. That's the thing, of course. There's a lot of information lost in this graph, but sometimes we don't need to know what resource it is. It's just the fact that there is a resource that they compete over. So this is the raccoon, also with the owl. I think raccoon also competes with squirrel. And okay, what about the shrew? It's rodents. These rodents kind of all want to eat the same kind of stuff, so they're connected. Although apparently opossum and mouse are not competing over the same thing. And then shrews seem to also want what woodpeckers want. I think this is the graph. I might be wrong. It's taken from a book from some. Oh, I know it's not. I think it's just they made it up. I don't know. So this is what a niche overlap is. So I repeat, an edge if two animals, if the two animals compete for the same resource. Yeah, compete for the same resource. I think it means in the book they say food, but it would even be other resources like wood or trees or something. That might also be. And so, okay, what's the purpose of this? Well, I'm not an ecologist, so I have no idea what you can do with this, but it does tell you something. It tells you that the type of food that you find in the forest is what squirrels like, and many others like this too. In other words, another question you could ask, for instance, is what happens if the squirrels are removed or like hunted or they die, there's some disease, and all the squirrels go away. This will open up a lot of food for raccoons and crows and opossums and woodpeckers. And this is always dangerous, right? If one species disappears, then other species all of a sudden have much more resources and therefore might become too, the competition is less strong, and therefore they might grow in numbers, which could bring the whole ecosystem into unbalanced. Okay, that's just an example. And so there's other things are tournaments that you can represent. As I said, I'm not gonna no longer give more examples. I want you to read them, and then we do a couple of simple homework problems, and then from next lecture on we will study this more. Would look more deeply into what is going on here.